This is TON 618. NASA currently lists it as the most massive black hole ever observed, with an estimated mass of around 66 billion suns. But here's the problem. That number isn't as certain as it sounds. Another analysis of the same object produced an estimate of about 40.7 billion solar masses. That's a difference of more than 25 billion suns. So which number is closer to the truth? And how do you weigh something you can't even see? Because after decades of studying TON 618, astronomers still can't completely agree on how massive this monster really is. And the reason why is far more interesting than simply calling it the biggest black hole ever found. Let's start with the number that made TON 618 famous: 66 billion solar masses. That's 66 billion times the mass of our sun, contained in a single black hole. To understand how absurd that is, consider this. The estimated total mass of all the stars in the Milky Way is on roughly the same scale. So at the higher estimate, you're looking at a single black hole with a mass comparable to the combined mass of the stars in our entire galaxy. Not a star, not a solar system, an entire galaxy's worth of stellar mass, concentrated into one black hole. And that's only the beginning. Mass is one thing, but what would something this massive actually look like in terms of size? TON 618's event horizon, the point of no return beyond which light cannot escape, could span roughly 2,600 astronomical units at the higher mass estimate. An astronomical unit is the average distance between Earth and the Sun. Neptune orbits at about 30 astronomical units. So the event horizon of TON 618 could stretch more than 40 times farther than the distance from the Sun to Neptune. If you somehow replaced our Sun with a black hole this massive, the event horizon wouldn't stop at Earth. It wouldn't stop at Jupiter. It wouldn't stop at Saturn. It would extend far beyond Neptune, deep into the outer solar system. And remember, that's not its entire gravitational influence. That's the approximate scale of the black hole's event horizon itself. So TON 618 has earned its reputation. It's enormous. But here's where the story gets strange. That famous 66 billion sun number is not a measurement made by putting the black hole on some cosmic scale. We can't do that. In fact, we can't directly see the black hole itself. So how do astronomers estimate its mass? They watch what happens around it. TON 618 is a quasar, an extremely bright active galaxy powered by material falling toward its central black hole. The gas around the black hole is moving incredibly fast, and when that gas emits light, its motion changes the appearance of specific spectral lines. By measuring those lines, astronomers can estimate how fast the gas is moving. Combine that with estimates of how far the gas is from the black hole, and you can infer the mass of the invisible object controlling that motion. It's incredibly clever. But there's a catch. The answer depends on the assumptions and the particular emission line you use. And that's where TON 618 becomes a measurement nightmare. One influential analysis using the hydrogen beta, or H-beta, emission line produced the famous estimate of around 66 billion solar masses. But a later analysis using a different emission line, C4, produced a much lower estimate, around 40.7 billion solar masses. Same quasar, same basic observational data, different spectral tracer, different assumptions about the gas, and a dramatically different answer. We're not talking about a few percent. We're talking about more than 25 billion suns. That's why saying TON 618 has exactly 66 billion solar masses is misleading. 66 billion is a widely cited estimate, but the true mass is not known with that kind of precision, and that uncertainty is the real story. There's another reason this gets so difficult. TON 618 is so distant that the light reaching us has been traveling for more than 10 billion years. We're not seeing the object as it exists today. We're seeing light that left it when the universe was much younger. It's essentially an ancient snapshot of a quasar from the distant past. And because TON 618 is so far away, astronomers can't simply resolve the black hole itself and measure its diameter directly. Instead, they have to reconstruct its properties from the light produced by the material surrounding it. So we're not weighing the black hole directly. We're watching the gas around it move and using that motion to infer the mass of something we can't see. Change the tracer, change the assumptions, change the calculation, and suddenly billions of suns can disappear from the estimate, and this creates a much bigger question. How did something this massive even form? TON 618 existed when the universe was still relatively young. That means its black hole had to grow to an extraordinary mass surprisingly early in cosmic history. And at these extreme masses, black hole growth becomes increasingly difficult for existing models to explain. That doesn't mean TON 618 breaks the laws of physics. It means something more interesting. Our models of how black holes grow are being tested against an object at an extreme end of the universe. And TON 618 is one of the most extreme tests we have. There's also something strangely fitting about how TON 618 was discovered. In 1957, Mexican astronomers Braulio Iriarte and Enrique Chavira cataloged it as a faint blue or violet-looking object during a survey of stars. At the time, astronomers didn't even know what quasars were. TON 618 was simply another entry in a catalog. It wasn't recognized for what it truly was until later observations revealed its enormous distance and quasar nature, a cosmic monster, hiding behind what looked like an ordinary point of light. And that raises a much more interesting question. If something this extreme could sit in our data without being understood for years, what else might we be looking at right now without realizing what it really is? And this is why TON 618 matters. Not because it proves that physics is broken, it doesn't. And not because we know with absolute certainty that it's the biggest black hole in existence. We don't. What TON 618 shows us is something much more uncomfortable. Even when we find one of the most massive objects humanity has ever observed, we can still struggle to determine exactly how massive it is. 66 billion suns, 40.7 billion? The difference is enormous. And somewhere beyond the limits of our observations, there could be something even bigger. A black hole more massive than TON 618, a quasar even more extreme, or an object that doesn't fit our expectations at all. We simply haven't found it yet, because the universe doesn't care about our records. It doesn't care what we call the biggest, and it certainly doesn't care how confident we are. TON 618 didn't just give us a record, it exposed how fragile that record really is. And maybe that's the most unsettling thing about it. The biggest black hole we've ever found might not be the biggest black hole that's out there. We just don't know. If you want to explore the biggest, strangest, and most unexplained objects in the universe, subscribe to Xplore Unknown. Because the most interesting discoveries aren't the ones that confirm what we already know. They're the ones that make us question it.